Cool. Okay, so I think like probably at least half the people who signed up are kind of here. So hello, I'm Richard. Very nice to meet you all virtually. I hope you're all keeping well given the kind of situation going on in the world. It's been strange being thrown into a kind of different situation, and what was going to be a in-person workshop is now a virtual one, but now with about 5 times as many people able to kind of participate and come along. So for the workshop, hopefully the resources are at least helpful to start with. And this is kind of a general kind of hello. And essentially a kind of opportunity to kind of chat in kind of real time and answer any questions that you may have, maybe go through some little demonstrations of things that may be not clear yet from the tutorials and so on. So yeah, so at the moment we have, I think, some of our esteemed presenters. So there's Sarah, who you can see at the top.
Hello, I'm Sarah, and I specialize in atomistic modeling, antiferromagnets. Yeah.
Okay. We also have Andrea Mayo. So you want to introduce yourself?
Hello. Well, I'm Andrea Mayo. I'm actually now kind of visiting in York, virtually visiting York, and yeah, so I've been doing dipole and constraint Monte Carlo, and well, lots of things anyway with Vampire.
Yep. We also have Andrew with us. I think if Andrew wants to say hi.
Hello, I'm Andrew. I mostly deal with rare earth ferromagnets, so the neodymium iron boron type ferromagnets.
Okay, I also have Daniel. If you want to say hi. Nope.
I can't hear you, Dan.
Nope, can't hear you.
Do you have your gain turned down on your mic?
See Daniel. Ah, participants, there we go. No, okay. Daniel there, so hopefully you'll see Daniel.
Can you hear me now?
Yes, we can hear you now.
There you go. Yeah, sorry, I was using the wrong microphone. Yeah, hi everyone. I mostly work with iron oxides and mainly magnetite.
Yeah, and I think our scraping expert is not currently here, but maybe on the way. That's Mara. So as Mara kind of appears, we'll say hi. But yeah, so thanks very much all for joining and kind of participating. So I guess where to start? Do you have any questions that anyone would like to put in chat? Okay, so actually we have one already, which is great. So will the recording appear on YouTube? Then yes, it will. So work. As long as we can get the technology working, that's the question. Okay. So are there kind of any questions on the kind of initial part, which is like atomistic spin models, or something on the Q temperature simulations, or visualizations, anything that kind of waiting for that. 50 questions appear immediately, but
well, I may start. I'm breaking the ice. So first of all, thank you for the organization of this series of informative videos and question time. So this is a workshop very well organized. Thank you. My name is Marco Asa. I work a bit on micromagnetic, mostly for teaching it. I actually teach micromagnetic simulation on a course at Politecnico di Milano. And I was looking now at, for the first time, at atomistic systems. So I always taught UNF, so micromagnetic simulations. And there, you know that the approach is completely different. So I have a couple of questions which relate mostly to the Monte Carlo versus, let's say, dynamic approach of simulation. The first one is the fact that when you do Monte Carlo, you set a fixed amount of steps. So you're never granted that the steps are enough, and you can also do the opposite error. So use more steps than needed. So you just slow down a lot the simulation. But I wasn't really sure that this is something that couldn't be thought in the way that I may be more used to. So just consider like some maximum allowed, let's say, variance or oscillation on the average value of magnetization, let's say, and tell stop there and stop your simulation once you got to a reasonable small variance of the average value. So could you comment on that?
Yes, so at the moment that's not implemented. It could be a feature that we could potentially add. Andrew's actually been working on a kind of statistical enhancements to Vampire, where we calculate, I think, the variance as a kind of, you know, is this good enough as a kind of parameter anyway. The downside with that is it depends very much on the kind of simulation that you do. So for example, if you have, just to say, a small ferromagnetic cube, then that approach is very clear because you have a single domain system and basically it's a ferromagnetic state and it's not going to do anything different. The downside comes when you look at, say, bigger systems where you may have domain structures that are metastable, or you have 2D materials, or you have you know, maybe nanowires, where again, the equilibrium state is maybe not so well defined and may actually be statistical in nature. And so in that case, the kind of, you know, you may miss the kind of the evolution of equilibrium ground state structures simply because you say, okay, this is converged. Whereas in reality, if you want it for longer, you may get the chance for those structures to fall. So in some cases, yes, I think that would be a very useful thing to add, and we can add that to the kind of pinned list of stuff to add in the future. But I think as a kind of general thing, assuming that will always work is not necessarily true. But I agree that, you know, you don't want to be doing excessive numbers of steps. So I think actually Daniel's a bit of an expert with doing highly converged calculations. Daniel, how many steps did you do as a kind of maximum for your very nice data that you got?
Is this what you mean for like magnetite, for example, and for doing the susceptibility?
Yeah.
In terms of just number of steps, for getting really nice curves of magnetization, I was doing around 1 million steps. And then an order of magnitude higher for getting our susceptibility.
So 10 million for the susceptibility.
Yeah, that was giving nice graphs. I mean, you could get very, you know, graphs you could work with less than that, but for really, really nice graphs that you could fit very easily, yeah, an order of magnitude higher. But the magnetization usually was not really ever a problem. Like 1 million steps with that material and with the sizes I was doing was very fast.
Okay. Yeah, so I think then in general, to answer your question, is kind of to get really converged data, you do need many, many steps anyway. Yeah, so statistical convergence may or may not be ideal things. I guess the other question actually is maybe near the Curie temperature, you may need more steps. So it probably also is temperature dependent. So again, having this thing might be a thing. So we'll pin that into the to-do list, I think. Yeah. To answer your question?
Yeah, absolutely. Thank you.
Okay. So, okay, so we've got another question from Nikolai on cobalt.mat. File folder with vampire distribution. Different style, not like a YouTube video.
I think I might have answered that a little bit later in the...
Oh, you have. Yeah. Oh, sorry. Okay, yeah. I added comments in the thing. Okay, that's fine. Okay. Command line comments options in Vampire. Yes, unfortunately, that's a big feature missing that we don't have. There is actually only one command line option, which I think is -F for input file name. But the actual commands themselves are basically listed in the manual. So we have now tied the manual version to the software version, so that hopefully in future these things evolve in step, so that as we add new features, the manual gets updated with the new features. So hopefully there won't be too much missing from what Vampire can do from what's defined in the manual. So yeah.
The source for the LaTeX manual is distributed inside the Git repository for Vampire. So if you clone the repository down from GitHub, then there is a manual folder that has the source for the manual in LaTeX. So you can build that, and then your manual will definitely be the version that is shipped with the version of Vampire you've got. The version on the website tends to only be updated at regular releases. So I think the version on the website of the manual is 5.1. I think it might be 5.0, but it won't get granular as granular updates as the GitHub will on the develop branch.
Cool. So yeah, so the question actually about alpha, which sort of is the sort of deprecation and evolution of input parameters for Vampire. So it's a more general question. So in general, try and at least save input parameters so that we deprecate them for one version and then probably delete them after. The point about them is to try and make them as human readable as possible without ambiguity. So alpha could be lots of different things. Damping constant is a little bit more definitive. So in general, with Vampire, we're trying to make sure that most of the input parameters are human readable. They're not the shortest thing to type in the world, but they should be hopefully reasonably accessible. Oh, actually, so also Mara has now arrived. So Mara is our Skirmion's expert. Mara, would you like to introduce yourself and say hi?
Hi, everyone. I'm Mara Strungaro. I'm a PhD student here in York, and I hope you already, or you will watch the Skirmion videos from YouTube. And if you have any questions, just write on Slack and I'll try to help as much as I can.
Thank you. So actually, in terms of the kind of format so far, has that been helpful? So having the videos and then having a kind of a chat channel, is that kind of working for everyone? Is there anything that's really desperate to have to kind of support getting to grips with Vampire?
So something that while people are typing out responses to that, something that we've maybe not been the most clear about is that we ran a similar workshop last year. That was an in-person workshop, obviously. Last year, the year before, last year. And that has a GitHub page with nearly all of the presentations that we've been recording, and also the input files for those presentations. If you wanted to test some input files that maybe are not as related to your field to see how Vampire works, you don't have to then understand every line in those input files because they are presented for you. And Richard has now dumped the link in the chat for that. That's a really simple Git repository. There's no extra branches or anything. It's just the files as they are. And every file should have a README associated with it to make it fairly easy to understand where you're going, even if you don't have somebody in person explaining it to you. So if you want to try some of the simple simulations that people like Sarah and Mara have been demonstrating on the YouTube videos, you can pull down, if not the same input files, very similar input files, and run Vampire on them.
Yeah, so from a couple of comments, it seems to be working okay. Did everyone manage to get the technology? Is there like a poll feature? Oh, there is. Can we get, okay, so cool, let's let's try this out. Ooh, I've gone somewhere else. A second. Okay. Right, I'm going to just do this on the fly. As
So I don't know how to pronounce your name. MCOM. When you say the different MIFTA, okay, how do you what do you mean by different NC moves? Do you mean the sort of traditional Monte Carlo and the constrained, or just the
Or do you
actual?
mean that it's Gaussian or spin flip or random movements?
Yeah. So if you yes, hold on. Yes to which person?
Into Sarah.
Yeah. That,
Get it right.
yeah. I think, well, Vampire uses 3 different types of trial move. If you have a spin that's pointing this way, one of them is just a spin flip, so it points up to down. One of them is Gaussian, so Gaussian peak, and then so it'll move mainly very close to where the initial spin position was. And the third one is random, so it'll just choose another random point on a surface. So I think, so this is just, I think it's faster at finding equilibrium values than just using Gaussian, because that's too small, or just using random because that's too big, and or just using spin flip because what if the equilibrium value isn't a spin flip? I think Richard might have more to add, but that's my understanding. Yeah.
Yeah. So actually, so historically, this came from a paper by Hinsky and Nowak, where they basically tried out a combination of these different moves and found that a combination of them was best. Last year, we published a paper actually where we developed an adaptive algorithm, which of course is not necessarily new; it's been done for years. But basically, we have a Gaussian move only, where we try and move in the vicinity of an existing spin position. But how close you move depends on the temperature. So if you have very low temperatures, then obviously, say if I have 2 spins here and I want to move one of them a little bit, then that has a very low energy if it's a small move. If it's a large move, then it's a high energy move. So if I were to say have a fixed width and I'm trying moves all over the place, then at low temperatures, this would be very inefficient. So most of the moves will be rejected. And so now we have a kind of this adaptive move where basically it will change the width of the cone so that at low temperatures, you look at a very small cone evolution, and at high temperatures, high one. But similarly also when you're, for example, doing hysteresis loops where you have a fast evolution of the spins, and in fact, you can also have a larger cone width to improve the acceptance probability. And so we did a bunch of tests and basically found that this was the most efficient over all the different moves or combinations of moves. And so that's now the default in Vampire. You can pick up individual moves if you want. So you can actually specify whether you want, I think it's sim colon Monte Carlo algorithm or dash algorithm equals spin flip to Gaussian, random, or adaptive. I think are the 4 choices. So you can actually, or must be a combination one as well. Hinsky Nowak maybe is the name of the combinational one. So there's those different options. I think they're all in the manual as well. But you can basically pick which algorithm you want. So for example, if you want to do an icing type simulation, then you can actually pick spin flip as your choice. So as long as you initialize all your spins, say along Z, then you can do an icing Monte Carlo very easily within that.
That's an interesting question, actually. You know, you might want to answer. So, can the properties in the material file be varied with time? And so I think well, as far as I know, in general, you can't really change properties dynamically as you run a simulation. However, what we tend to do if we need to see how a system changes different properties is we'll run a simulation, and then you can use a few parameters to save the end state of that simulation and then continue it after you've changed those parameters in your input and material files. Of course, it would be a bit difficult if you really want to have like a fine change of those parameters, I think. Is that right, Richard?
Yes,
Yeah,
Joe.
so what I am actually planning to do, right, like applying voltage, I just want to change the anisotropy constant at every time step. Like I'm running 10,000 time step. So 10,000 steps. So each step, there will be a gradual variation in the anisotropy. That means the form you build the .mat files, I say it cannot be changed because for all over the time steps, it considers all the constant, all the properties to be constant for the running time. But earlier, the magnetic software like Mumax or others I was using, I could just simulate this property like a time variation of this constant.
Okay, so actually, you're not the first person to ask this, and so I think it's maybe again something to kind of pin in the to-do list. So in general, for all properties, it's a bit tricky because some things are kind of set up in a kind of particular way within the code. In the meantime, you can actually go in and, you know, if you want to hack the source code a little bit, the actual the program part is actually relatively straightforward to kind of modify. So for example, you could insert something very easily in the source code and recalculate the anisotropy as a function of time in there. In general, we could try and add some support for that as a specific option. So if you specify maybe a file of times and constants, and then we can kind of just load that in and then interpolate that to give you a time-dependent anisotropy, for example. That might be a way of doing that. So it depends on how quickly you want that done. If you're doing it, then it's going to be much faster. If you want to hack the source code, we can help you do that. Or if you want to, as a feature, it will take a little bit more time, but certainly something we can do reasonably quickly.
Yeah.
So something to be aware of with that is that if you have different anisotropy constants, then your equilibration time could be different. And so it might not be as simple as, you know, every 10,000 time steps increase anisotropy by 1% or something like that, because then you're actually going to be losing a lot of time. You know, if you have a very, very high anisotropy constant, then the system's going to equilibrate very quickly because there's a lot of energy forcing it in a particular direction. And so your other end of your simulation, you'd be not necessarily equilibrated, or you'd go the other way around and you'd make sure you're always equilibrated, and then you'd be wasting time steps at the other end. So it's something that is actually, it's sort of relatively easy to do, but to get it to be efficient is slightly more difficult. So that's something to be aware of. If you're running a simulation that isn't going to be particularly expensive, then it's not worth worrying about. But if you're running a very large simulation that could be, you know, days of computation time, you could be wasting a lot of CPU time if you aren't careful.
So there's a question related to the unit cell file, related to the last three parameters. So you have the material ID, category, and height category. So with the material, basically you can introduce different magnetic properties inside your unit cell. So for example, either if you want to have different magnetic materials with different anisotropy or damping and so on, so you can introduce that into the unit cell file. The other option, the category and high category, is related to, you can have like the same material, but different maybe spatial configurations. I haven't used this feature quite a lot, so maybe Richard can explain it better, but it's useful maybe if you want to model things like core shell structures where basically maybe you have the same material but just different spatial configurations?
So actually, we didn't yet implement the category in the statistical analysis yet. So it's there for kind of in case we did that in the future. But the height category is implemented. So for example, if I have maybe a nanowire and I wanted to look at how the magnetization varied throughout that, it's possible to actually output the average magnetization in each unique plane of atoms in that nanowire. The downside is that you produce very, very large output files, which are quite tricky to kind of manipulate and get your head. You need to basically write some code to take the data and analyze it. But that facility exists, but it doesn't yet exist for the general category. So the standard way of doing that is actually to have different materials for different elements. So for example, core and shell, you might have different materials for that. And then you can then plot the magnetization for each component as you like.
To be clear, when he says different materials, he means different materials in the files. They don't necessarily have to be different. It doesn't have to be iron and something other than iron. You can have two different materials with the properties of iron, and the statistics for them will be done separately, as well as in total. And then they'll be output as separate columns with separate headers, so you can pull them out programmatically. If people want, we can have a look at that at some point, or I can maybe arrange a small sort of tutorial thing with regards to pulling this data out in something like Python, so you can look at your thousands and thousands of layers of heights without having to do it by hand.
Okay, so I have a question from Oksana, and related to what happens if the number of time steps too large. Is there a maximum limit?
Should give an error.
Yes.
10 to the 7 steps, I think.
Yes. So in general, for most systems, that is excessively long and will not be feasible for anything more than a few atoms. Can you elaborate, Oksana, a bit on that issue with the, did it run out of computation time or something, or was it just like on your desktop, or in principle, I
think if you did start, shouldn't be having any issues in terms of number of steps, because that would cast an error. But maybe it did run out of time, computational time, maybe. No?
Did you get any output? Did you get any output past the header? Because if it could be that it's just taking it worked for about half.
I got an output. And well, maybe it'd be worth. Would be good to see the log file, maybe, so we see what's the last thing that the code kind of did.
So
yeah, if you can
maybe post the kind of a very simple input that kind of has the problem to maybe the Slack channel. We can kind of have a discussion there, or if we have a look and discuss that as well. But again, if it's public, then everyone can also sort of see the answers and see how happens that. But sometimes it can be something that's either Vampire's been a bit weird and does something a bit strange, or some sort of technical issue with the input file. But
was there not an issue sort of the end of last year with OpenMPI 2 if you ran a simulation for a very, very long time?
Yes, there
It
was.
turned out to be OpenMPI's implementation, like it was their end, wasn't it? And
Yes.
that crashed only after hours and hours and hours of work, because it was getting to a bit of memory that wasn't looked after properly.
Yes.
And that was, so it might be that you've got, it might be a bug in OpenMPI. Was this in parallel or in serial? So it might be the version of OpenMPI, because that was an OpenMPI bug, and obviously we can't fix OpenMPI. So it might be worth looking at the logs for that. If you could put any of that in the Slack channel, we can have a look at it.
Yeah, I think version 1.8.3 of OpenMPI was fine, and version 3.18 or something like that was also fine. The ones in between there had some bug with memory management. So basically the messages would kind of get queued up but not deleted properly. So that was one issue we did have last year. So version 3.1 point something seems to be okay. 1.8, the old one, is also fine. The 2 had some bugs that, yeah, so that might be another issue. But if you post the inputs anyway, we can have a look at that.
I saw a question from our Mac on the unit cell. So the unit cell in Vampire is the minimum units of atoms that you use to actually build your crystal structure. So for a simple cubic, you just need one single atom, and this will be replicated within the space and will give you your structure. So this also means that if you want to do anything more complicated, a unit cell must be including every atoms that you will need. Also mind that in Vampire, the way the unit cell is replicated is very important. So you just have a translation along so that your translation vectors are just along the X, Y, and Z directions, which means that your unit cell must be built and containing atoms such that when you apply these translations, you will actually obtain your crystal structure. These might, for example, and the classical example is if you think about an FCC system, and you are maybe familiar with any ab initio, with any ab initio code, you would see that the unit cell would be slightly different because you use different translations vectors. Does it make any sense, the explanation? Or Richard or anyone else doesn't want to add anything?
So also it depends on the what needs you have. So even if you can reproduce your system with less atoms, but if you want to have more insight about different magnetic properties of inside that unit cell, so you can make your unit cell slightly bigger. In this way, you can use the material parameter in which you will get the better statistics on different atoms from that system, such as in antiferromagnets.
Okay. So I have another question actually about spin accumulation. Spin transport is a frustrating issue with Vampire. We've been trying for many, many years to get something that consistently works. At the moment, I believe there are 2 different implementations available. The first one is the original one, which is what is in the thesis. So I think Andrea would like to kind of, I think we'll do tests on that. And
you mean the Andis Lanzewski one?
Yeah.
Yeah. Well, one implementation uses the Lanzewski approach, which it was originally a macrospin approach and has been then adapted to a macromagnetic level. So the idea is that you describe the spin transport having just on the layer on the material where you assume the polarized current is being injected, and then you will simply have the cross products between the magnetization and the injected current direction, and then everything is down to parameterize in the best way possible the coefficients that will give you substantially the magnitude of your torque acting on the magnetization. Now, in this approach, even though you apply to each single atom individually, each single spin individually, there are limitations, or because you actually neglect the fact that the properties will be different. Or if you want to you inject your current, not necessarily all the system will be subjected to the same current density, well, actually spin density. And so I did use it. You can, so at the moment, this approach allows you to get good results, but if you want to be very accurate, or especially if you care about also the high temperature dynamics with spin current, with this approach, you might end up usually overestimating the effect that the injected current has. But you could take it as a first and rough approximation of how the spin current works. But I was wondering whether the comment was referring, maybe read the thesis from Noy, because I do mention spin accumulation, but very little. In reality, in this approach, you don't really you kind of hide all these the spin accumulation part, and you just end up having your torque and everything is hidden in your coefficient. So I wonder where actually the comment is about the spin accumulation as developed by Noy. Does at the moment the comment satisfy, the answer satisfies the comment or question?
So we have another question actually. So I think that's good to need to know anyway. So another question about whether you should use two sublattices in the UCF file for a particular system with competing ferromagnetic and antiferromagnetic exchange. In general, I would say yes, this is a good approach, because if the state is unknown in the sense whether it's a ferromagnet or an antiferromagnet, then it's probably better to calculate both properties, so basically the magnetization, but also the sublattice magnetization, so that you can then verify how both are behaving with time. So maybe it depends on the anisotropies that you may have, or you may have some competing ferro and antiferro exchange that in fact may give you kind of different regions of space where you have different ordering. So in general, I would say it's good to produce more data than you need, and yes, having two sublattices in the UCF file will be a good approach. If you know what the site symmetry is, and you can say, okay, it'll be a two sublattice antiferromagnet or a ferromagnet, then that would be a good way of doing that.
I see.
So,
oh, sorry, go on. Go ahead.
Can I answer the question related to the inbuilt DMI? So the inbuilt DMI, basically, this feature calculates the interaction that it's mediated by some other type of atom. So you can have a DMI not just for a single layer, it can be for multiple layers, so for the full material you're trying to simulate. But just have in mind that that the Jaushinski-Moriah strength will be calculated with respect to a different atom, the atom that will mediate this interaction. So in principle, you can, with this option, with the inbuilt DMI option, you don't need a unit cell file. So this is why it's a bit easier to use. However, you need to construct it more carefully to see what type of atom will mediate your Jaushinski-Moriah interaction, and as well, what's the cutoff you want to include for this interaction, and so on. So you can do for full materials without the UCF files.
So if we consider the platinum as the non-magnetic layer, then the interaction of the first layer with this non-magnet will be different from the second layer with the non-magnet, right?
Yeah,
so,
because they're farther apart.
Yeah. So do I need to input separate DMI value for this second layer?
It's up to you. Would you like to have so both layers will interact with the amine both layer will be given by the platinum layer, but the strength will be slightly different. So it's up to you if you want to have the same strength in the two layers or different, or this strength to vary with distance and so on.
Okay. Thank you.
So I think Daniel's sort of replying in text to one of the questions on using magnetite and the spinel structure. So this is kind of something which we've embarked on in terms of trying to improve support for more complex crystal structures in Vampire. So for many years, we only had sort of simple cubic, FCC, BCC, and so on. But now we're looking at things like, so spinel, we've got in rock salt structure, which is a very simple cubic antiferromagnet. Plus to come, I think is YIG maybe, and probably neodymium boron, for example. So in future, we're going to build all these into Vampire so that it's a kind of a one-liner to define the crystal structure and then get things going, at least for common materials. And the idea being that it avoids having to go into this kind of journey to understand UCF files and get all the interactions there and having to write code to do that. So basically, Vampire should do all of that at the front end eventually. Obviously, if it's more complicated, so you have a multi-layer structure with, say, 2 different crystal structures, then you still have to go in and define that. But hopefully for bulk materials or single type materials, single crystal materials, this should all be built in the future.
So it might be worth mentioning when you should be on the master versus the develop branch, Richard, because that tends to be a confusion, because obviously when you clone the Git repository, you end up with master as the default, or master as the default, and we don't tend to do most of our work on the master branch itself. So it might be worth explaining just the difference in philosophy between the two branches, because it might not be the same as other open source software packages you've used.
Yeah, thanks, that's a good point. So so in Vampire, essentially we have 2 kind of active versions. The first one is master, which is an occasional release after usually a year to 2 years, where we kind of develop is then stable and well tested, and we're very happy with all the features in that. But typically the features lag behind quite a bit. So as we implement new things, we implement them in a separate version called develop, where essentially then we add in new features that may not be entirely kind of bug-free, but are generally okay for production use. So most people in the York group, at least, use the develop branch for their main production work. And so it tends to be stable enough for that, but also includes the latest features. So, but a lot of things that we're talking about in the workshop will use these latest features in the develop branch of the code. So I forget whether I defined in the compiling Vampire tutorial whether I changed branches or not. But in case I didn't, you can do git checkout -b. I'll write this in the comment. Account -b develop. So in the Vampire source code, if you type that command, then you will switch branches from the default master branch to the develop branch. And then if you recompile with the -b capital B option, so for example, make serial -B, that will recompile from scratch and then have the developed version of the code, which has new features that aren't in the master branch. Oh, sent to the wrong person, sorry. Try that again. There we go. There we go, try that again. Any open questions that we have not answered yet?
I think it might be also worth saying that later in the week we're going to have, specific sessions on the later videos. So if you have questions related to like antiferromagnets or skirmions. We'll have more sessions for them as well.
So it's kind of expected. I mean, this is kind of, general questions about Vampire. So, for these specific sessions, we can go into a lot more depth in terms of, those particular topics and of interest, hopefully to maybe only a subset of you, but, hopefully provide more support of those particular things. So also one more question from Encom. So heat capacity is implemented, so you can output specific heat capacity. Bin accumulant was an oversight. We can add that to the list of things to add. I imagine that's relatively simple to add. I'll talk with Andrew maybe about that. And it's just kind of a subset of the property. So that was probably useful to include, definitely. So another question also about mean field type interactions. Can you elaborate a little bit about what you mean by that?
So the bind accumulant is a kurtosis parameter, I think. So in principle, shouldn't be particularly difficult for us to implement, I don't think.
Okay. So just to finish off the comment on the mean field interactions first. So we did try that, but there were some numerical instabilities in that. So what we had wasn't working. So for example, an average dipole field, I tried that some years ago. I wasn't particularly satisfied with the accuracy of that. So apart from dipole fields, there are kind of no long range mean fields. But obviously, if you want to include, say, an average magnetic field everywhere, then that's obviously doable with a global field. In terms of kind of correlated interactions, not so much at this point. Okay. Another question, there is a command to generate a temperature gradient.
Is it? I don't think it's implemented yet.
No, I thought I did that.
I mean, you did it because we did it at some point, but I think we just hacked the version.
I think
we put it in a release. I'm not sure.
Let me have a look. So I can't answer that question yet as to whether we implemented the temperature gradient. I think I did, but I'll have a look for that and put it in the Slack. I don't know to look at that in a minute. Okay.
Who asked the question?
So Mahadeen has a question about simulating disordered systems. Inherently, with temperature, you can generate disordered systems. You can also simulate sort of pseudo-amorphous systems because you can randomize whether or not a particular atomic site is one material or another. Obviously, if you begin by aligning all of your spins, then your spins will all be aligned, but you can also have your spins start in and not aligned or in a non-equilibrium position. So yes, you can generate several different types of disordered systems depending on what you mean.
Just seeing the question from Matthias regarding the fact it doesn't get any output.
He asked about WSL, which in general shouldn't be giving you any problems on output. Are you referring to just the plain old output data file, like literally called output, or are you referring to
yes.
It's weird.
So
It's on screen.
Does ls in the terminal give you the actual output file, or is it something that you can't find out on Windows, the Windows side of it?
So have you
Or is the
got
output rate, maybe?
Well, there's the output rate, and so you've got obviously screen mean magnetization length to send to the terminal. Have you got it set to output? Sorry, I haven't seen if you said this already. Because output and screen go to different places. Screen goes to standard out, and output before the colon in the input file sends it to the output file. So if you only have screen mean magnetization length, then it won't go to the output file. I can actually just check the tutorial file for a sec and see if what the defaults are for that.
So it could be that, so the Windows subsystem for Linux has a different file system to Windows, so that may be one issue if you can't find that. The folder for the actual home file partition is buried somewhere in Windows system.
Yeah.
So it's a bit awkward to find it.
As a heads up, if you're using the WSL, a general thing that's good and doesn't mess up your files without you realizing is if you move, for example, your vampire source or whatever you're working on, if you do that on Windows, as in on a Windows directory, and then find it through the subsystem, normally you do that by doing change directory / mount, and then it should be your drive name, etc., then you can work on it in Windows subsystem for Linux, and it will also behave well in Windows. So you can actually open it with whatever editor you prefer in Windows if you do things that way. It's slightly dangerous to work on, like, even if you're like writing code for Vampire, it's a bit dangerous if you try to edit that from Windows if it's in a WSL directory, just because of how the two file systems work.
Yeah, so I think the discussion about this, again, is good to maybe move to the Slack channel where we can kind of have a more detailed discussion about the kind of ins and outs of that. Yeah, it sounds like a weird bug. So I haven't tried to fix that one yet. Cool. So, are there kind of any last general questions that everyone has, or we can kind of just wrap things up a little bit? So hopefully there will be many opportunities over the next week anyway, or a few days, to ask many more questions and questions. But in terms of the poll, it looks really good. So I think almost everyone has pretty much got the technology working with command line, so that's good. If you don't, then yeah, please just get in touch via Slack and have a discussion there about that. Parallel version, it is, despite not being that much faster in the actual video I was recording, it is in general much faster for large systems. So it is definitely worth struggling through if you can to get the parallel version working. But again, if you get stuck, please do feel free to ask questions in the Slack. Okay. So in the absence of kind of a flow of new questions, we can kind of wrap up the first session here. I think we will have another one for those who have any specific questions about visualization in a minute or two. So I think Andrea and Daniel are going to lead that, but I will also be kind of hanging around as well.
Yep.
And then I will also sort out a schedule for tomorrow as well, and also another video playlist for tomorrow in advance to kind of have a look through and see what's kind of coming. Cool. But other than that, well, thank you all for coming along, and yeah, hope to see you again later on in the week. So thanks everyone. Take care.